Let's say we want to see if a number is prime, which is important in cryptography. We can use a test called the Miller-Rabin test to do this. The Miller-Rabin test is as follows, displayed on the screen. Okay, that's a lot of gibberish, so let's dissect this. This sentence says that we factorize n-1 as 2 to the s times d, where d is odd, and this sentence here says that we pick a number a less than n. We then say that n is prime if a to the d is 1 more than a multiple of n, or a to the 2r times d is 1 less than a multiple of n, for some r greater than or equal to 0 and less than s. If n does not satisfy at least one of these conditions, then n is definitely composite. Alright, we now at least understand the test, but it still doesn't make any sense. Why does this test determine if a number is prime? Well, let's show that all primes actually pass the test. So let's say that we have the expression x to the 2s times d minus 1. We can repeatedly factor using difference of squares to get this nice expression, and so we now evaluate when this number is divisible by a prime number. Well, this means that one of the factors must be 0 mod p, so either x to the d is congruent to 1 mod p, or the rest of the factors are negative 1 mod p. So this can be condensed into x to the d is congruent to 1 mod p, or x to the 2r times d is congruent to negative 1 mod p, for 0 is less than r, which is less than s. But this is the same test as we defined previously, and so this means that the test is related to primes. But there's something else that's important. The Miller-Rabin test isn't actually always correct. In 1978, it was shown that there was a 1/4 chance that the Miller-Rabin test identified a composite as a prime. But we can fix this. Rather than picking one value of a, let's say we pick k different values of a. Now we can run k different iterations, and this means that the probability of a composite number passing is 1/4 to the k, which becomes extremely small very quickly. And so there you have it, the Miller-Rabin test.